talked about functions of more than one variable. Next time we want to talk about calculus of functions of more than one variable. We'll start off just by a little review of sketching. Unfortunately, functions of more than two variables are hard to sketch, right? What we said is in calculus 1, you have a function of one variable, you can sketch it in the plane by sketching points x, f of x, coordinates x, f of x in the xy plane. And for functions of two variables, you can sketch points in 3 dimensions. For functions of two variables, you plot over each point xy in the xy plane. Here's x coming out of the board, here's y, and here's z. For each point in a given domain for the function, there's some plane region where a function of two variables is defined. For each point, you go up z equals f of xy and plot a point, xy, f of xy. The collection of all those points forms a surface over the domain in 3 dimensions, and that's how you sketch a function of two variables. Trying to sketch them in more dimensions actually can be done. There's a very fascinating video online that you can look up, drawing in more than 3 dimensions. But in practice, it's so hard to read that nobody does it. So we'll just say that we don't want to sketch in more dimensions. We'll do these theorems for functions of two variables, and then there's a completely obvious extension to functions of more than two variables. So today, calculus of these functions of two variables that visually you can think of as surfaces over the domain of a plane region. So now, one thing we want to do in these sketches is say, and this applies to higher dimensions too, how can we sketch these, how can we get a handle on these in another way? Well, we could think of intersecting these surfaces with horizontal planes. I could cut it, and if I cut the surface with a plane, I'll get a curve of intersection. I cut it up here, I'll get another curve of intersection. And each of those curves is called a trace. When you intersect a surface with a plane, and if I take traces from horizontal planes, and then I project those curves down to the xy plane, the projection of those in the xy plane are called contours. And the collection of all of those is a contour plot. So we'll say, if we intersect z equals f of xy with a horizontal plane, z equals k, and then project it down to the xy plane, that trace projected in the xy plane is called a contour. And the collection of those, any set of those, is a contour plot. So here's an example. Suppose I have this gnarly function here, z equals square root 64 minus x squared minus 4y squared. Maybe I don't know how to plot it right away, but maybe if I did some contour plots, some contours of these intersections, I could get an idea what it looks like. And by the way, this contour plot, what it really is, it's like a topographic map. You've seen those of mountains, right, where they show the isopleths, the contours of constant altitude, and you look at the rings of constant altitude, and you can figure out kind of what the mountain looks like. That's what a contour plot is. It's like a topographic map. So we'll draw a topographic map for this one and figure out what it looks like without having to draw the surface maybe, although this surface we can draw, and I'll put it up shortly. So let's intersect this surface, f of xy equals square root 64 minus x squared minus 4y squared, with a horizontal plane z equals 0, the xy plane. Right? Then you just replace z with 0. We call it the k equals 0 contour. And we get 0 equals square root 64 minus x squared minus 4y squared. That might be hard to sketch too, but at least it's in the xy plane instead of in 3 dimensions. Right? Each contour is a curve in the xy plane. So how can I sketch that? Maybe I'll square both sides. Get 0 equals 64 minus x squared minus 4y squared. And then if I add x squared plus 4y squared over to one side, I get x squared plus 4y squared equals 64. I know what that is. I'll just divide by 64 and get x squared over a squared plus y squared over 4 squared equals 1. That's an ellipse, right? X squared over a squared plus y squared over b squared equals 1 is an ellipse with semi-axes A and B, or in this case 8 and 4. So I can draw that in the xy plane, this nice contour, without even having to sketch the surface. Now let's try sketching another contour. We'll take the trace by putting k equals 4 and get 4 equals square root 64 minus x squared minus 4y squared within the z equals 4 plane, then project it down to the xy plane and get this contour. How do we figure out what that looks like? Let's square both sides again and divide by 16 this time. Now we'll get x squared plus 4y squared equals 48. And we also have to subtract, we square both sides, subtract 16 and get this. And then we'll divide by 48 and get this, right? X squared over 4 square root 3 quantity squared plus y squared over 2 square root 3 quantity squared equals 1. This is 48 and this is 12. So you get another ellipse with semi-axes 4 square root 3 and 2 square root 3. Now we'll intersect it with the plane z equals 8. The k equals 8 contour we get is 8 equals all this. When you square both sides and subtract 64, you get x squared plus 4y squared equals 0. That's a single point, right? The only way you make this true is make x and y both 0, since these are both non-negative terms. So now this time the intersection is the point 0, 0, and we have 3 contours that we can plot within the xy plane. So here they are. The ellipse with semi-axes 8 and 4, the ellipse with semi-axes 4 square root 3 and 2 square root 3, and the single point. This is my contour plot, and now I have an idea that this mountain kind of sticks up, if I had Z coming out of the board, kind of sticks up like this, with higher and higher levels that are all, like you could have horizontal trails that were all ellipses. Right? Now, really in this case, we know what the surface looks like because this is one we've seen before. If we again write Z equals square root 64 minus x squared minus 4y squared, and square both sides, we can write this actually as an equation for an ellipsoid. Right? It becomes, what, x squared over 64 plus y squared over 16 plus z squared over 64. So it's an ellipse with semi-axes 4, 8, and 8, I guess. So you come out here 8 along the x-axis, 4 along the y-axis, and actually 8 along the z-axis. And you can make the ellipsoid, and now you can see exactly what happened, how we generated this. We intersected with the plane z equals 0 and got this trace, which projects to itself. We intersected with the plane z equals 4, got this ellipse, and we projected it down to this one in the xy plane. The plane z equals 8 just touched the top of the ellipsoid, projecting down to this single point. And so there's the here's the surface, here's its contour plot, and these 3 curves here are the traces. Software such as MATLAB or Octave, which is a free version of MATLAB, you can just download it for free from the new GNU software site, and you can make beautiful, beautiful plots of surfaces and contours. It does take a while to learn the language, but once you know it, you can make beautiful computer-generated plots of these things. They're quite good at it these days. Now, we want to do calculus with these things. Oh, that was the warm-up for today. How about that? The calculus isn't hard yet. We're just starting it. To introduce calculus, we first want to look at limits, right? Calculus and functions of one variable. You started with limits. That allowed us to define derivatives and integrals and asymptotes, all those calculus concepts. Let's do that again. We said this will be multivariate calculus, similar things to calculus 1, just done in more dimensions. We're starting that today. Limits and continuity, I want to remind you of this hard concept. You don't have to be good at this, you just have to have the concept, all right? Because we aren't, just like calculus 1, we aren't going to prove things with these definitions. We aren't going to evaluate limits with these definitions. We're going to have some theorems that are proved using these, and then you use the theorems because it's too hard to use these definitions to actually evaluate the limits. But you want to see these so you know when the limit exists by inspection and what's going on to prove the theorems. Some of you math majors that need these for other things later. Here's calculus 1. When you had a function of one variable, and you wanted to say, what's the limit as x approaches x0, some number of the function of one variable? How can I say that's equal to a number? This was the definition you gave, the epsilon delta definition, right? If for each epsilon greater than 0, a positive number you give me, there exists a positive number I find, delta, such that if x minus x0 is between 0 and delta, then f of x minus in absolute value, then the absolute value of f of x minus L is less than epsilon. And then we said, that looks like garbage, right? Well, garbage in, garbage out. Now in calculus 4, look, if for each epsilon greater than 0, there exists a delta greater than 0. You give me any epsilon, I find a delta, such that whenever 0 is less than the square root of x minus x0 squared plus y minus y0 squared is less than delta, then the absolute value of f of two variables, f of xy minus L, in absolute value is less than epsilon. Then we'll say, that's off the bottom, isn't it? That the limit as a function of two as xy in the plane approaches x0, y0 of the function of two variables is L. This is very different because in the plane you can approach x0, y0 from lots of different ways, right? In this one you could approach from the left and right on the x-axis, getting closer and closer, marching along the axis to x0. Here you could spiral towards the point x0, y0, or approach from all sorts of different directions along different curves. And so this is a pretty tricky concept, but it has a fairly straightforward, just like what you saw before, definition. And it doesn't matter which way you approach, it turns out, if the limit is equal to L, then the limit along all the paths will also be equal to L, is what this definition encompasses. So this is an important definition right here. Now, that all looked like garbage, unfortunately, right? Nobody understood what the limit was from that. So let's draw a picture, and the picture might make it better. Just look at the concept across, I hope. In calculus 1, you have this. If you want to show that as you get marched along the x-axis closer and closer to x0, the limit was this number, y equals L, but I should put an L here. How could you show it? You said, I just say to you, you pick a small positive number epsilon, no matter how small, and I'll go epsilon units above and epsilon units below. I can find a piece of the function that's that close by finding a number delta small enough. So I pick it, if you pick, this is epsilon here, epsilon above the line y equals L, epsilon below, then I just pick this delta here to go this distance on each side, and if along this thing, omitting the point in the middle, because the function doesn't have to be defined at the point, just on some interval on each side, if no matter how small you pick epsilon, I can find a delta such that this piece of the function between plus and minus delta on each side stays within those two lines, then we say the limit's L. And you say, well, that's not fair, I'll just pick epsilon smaller. Well, you pick epsilon smaller, I just pick a delta smaller such that the function squeezed that close. And what you see is this definition shows that I can squeeze the function arbitrarily close to this line y equals L by picking delta small enough. No matter how small you pick epsilon, I can make the function that close. We do exactly the same thing here, except we squeeze it between two planes. If I want to show the limit of the surface is a point z equals L, I draw the plane z equals L, and a surface z L plus epsilon, z equals L minus epsilon above and below it, and you say you have to squeeze all the z coordinates within distance epsilon up above or below, no matter how small I pick it, fine. If you pick epsilon this small, right, epsilon above and epsilon below, I just pick this little disk, and I say if you're within this distance in 2 dimensions, right, this is distance in 1 dimension delta. If I'm within a distance delta on either side in 2 dimensions, that's a disk. This really should be an open disk, don't include the boundary, but it's hard to see it if I draw it that way. If I'm within the inside of this disk, on the a surface, all those points will be squeezed between the two planes. And if no matter how close you squeeze those planes, I can capture the image of my little disk, some positive radius disk between those two planes. We'll say the limit of the function of two variables is equal to L. That's the concept. I squeeze it as close as you want to the planes equals L by picking a small enough disk now. And you can imagine in more dimensions, if a function of three variables, then you have to squeeze the sphere, by squeezing a small enough sphere, I can sit between two hyperplanes in 4 dimensions. This is one of the fun things that Calculus 4, you get to talk about multi-dimensions and shades of Star Wars and so forth. So I can, by picking a small enough sphere, squeeze between hyperplanes in 4 dimensions. Close enough. All right, so that's all fine, but who wants to prove anything by these klutzy definitions? It's too hard. But we do want to make this definition, just like continuity was important for lots of your theorems in Calculus 1, now we want to say, what does continuity of a function of two variables mean? We'll do the same thing. We'll say, if f is defined at the point x0, y0, and the limit exists as xy approaches x0, y0, and the two are equal, then we'll say it's continuous at that point. So the function is continuous at a point if the function is defined, the limit exists, and the two are equal. Now I won't write that all out here. With it tacitly assumed that the thing has to be defined and the limit existing, then you just say if the value of the function is equal to the limit, that's what we call continuity. Continuity in function of two variables or one means that you can evaluate the limit by plugging in. That's what continuity means. Right, you just plug in the point to get the limit. So those are the nice functions. When you see those to evaluate a limit, you just plug in. So now, what nice theorems did you have? We won't prove these here. They're very tedious and actually very easy, but we don't want to take all that time, right? We'll just say that polynomials in multiple variables are continuous, just like polynomials in one variable are continuous. What does a polynomial in more than one variable look like? Well, let's look at that briefly here. Examples. Here's some polynomials in two variables, x and y. Remember, for polynomials in one variable, it's a number times the whole power of x plus a number times the whole power of x plus dot 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 plus a number. That was a function, a polynomial function in one variable. Now we'll have a number times the whole power of x times the whole power of y. Think of y to the 0 here. Plus a number times the whole power of x times the whole power of y. Plus a number times the whole power of x. Think of x to the 0 times the whole power of y. Same thing here, same thing here, something here. Plus a number. A function of that form is a polynomial in two variables. So here's one, here's another one, right? 4 times x squared times y cubed plus 3 times x times y minus 1. Whole powers of x, whole powers of y multiplied together times a number, all added together. Those are polynomials in two variables, and they're continuous everywhere. Function that's continuous at every point, we just say it's in its domain, we just say it's a continuous function. So we'll say polynomials are continuous, meaning they're continuous on their domain, which is the entire xy plane. Right? And now to evaluate limits, right? What's the limit of this quotient here? What a mess. How can we do that from that nasty epsilon delta definition? We'd be all day doing that, right? Trying to figure out some way to prove that, with a little disk we can get close enough. Instead, we'll use this wonderful theorem. On the top, this is a polynomial in two variables. This, on the bottom, this is a polynomial in two variables. Those polynomials are continuous, and furthermore, we know that products, quotients, sums, and differences, except where quotients have denominator 0, are again continuous, and a continuous function of a continuous function is continuous. So we'll say, here we have a quotient of two polynomials. The top and the bottom are both continuous because they're polynomials. Therefore, the quotient is continuous as long as the denominator is not 0 at the point we're going to. Well, we're approaching 1, 3. The denominator is not 0. So what's good about polynomials? You evaluate their limits by plugging in. You plug in 1 for x and 3 for y. 1 squared plus 3 squared on the bottom is 10. 1 times 3 on the top is 3. This limit is 3/10 just by plugging in. Easy cheesy, right? Now, what's a little harder in calculus 1 if it's a 0 over 0 case. Let x, y approach 1, 1, and you get 0 over 0. Now what's the limit? Remember? One way to do that was factoring. So we'll factor the top. This is the difference of squares. Factors is x plus y times x minus y. We can cancel x minus y with what's on the bottom and see that this limit is actually equal by canceling to the limit of x plus y, which is now a limit of a polynomial we plug in. 1 plus 1 is 2. There we go. So there's an easy limit evaluated after canceling. I know this is going a mile a minute. Just rewind and look at it. Here's the idea. I would go slower if this was a lecture where you were writing down the notes. All right, the limit as x, y approaches 0, 0 of square root x squared plus y squared times ln square root of x squared plus y squared. Now we're worried because even though square root is a continuous function, so this is continuous, and this is a continuous function, ln is, within its domain, there's a problem here because we're right, and when we approach 0, 0, this is the boundary of continuity for this. It may not be that we can approach from all different directions in the plane and still get the same number, because this is at the boundary of continuity of the square root function. So we're going to have to try something a little more clever here. Also, ln is approaching, it's a point where it's not even defined. So what is this? Maybe the limit is actually infinity or something. Let's try it out. Here's a trick. In some cases, you can make a change of variables. This looks like polar coordinates. X squared plus y squared is r squared in polar coordinates. So we could say this is limit of square root r squared, limit of ln times ln of r squared in polar coordinates, where r and theta are going, r goes to 0 and theta arbitrary. So we can drop theta out and say this is just the limit as r goes to 0 from the right. What we're doing is we're approaching the origin. We can use positive r, and we only approach from positive r. Square root of r squared, ln of r squared, is the way this rewrites in polar coordinates. And now, what can we do with this? Well, square root of r squared is actually absolute value of r, but since we're letting r approach 0 from positive, we can replace this with just r. And now, ln of r squared, remember you can pull the 2 out, is 2 times ln of r. So it says 2 times ln of r. I'm sorry, it's off the edge. So we have 2 times limit of r ln of r. What could that be? Well, unfortunately, r is approaching 0, and ln of r, as r gets closer and closer to 0 from the right, is approaching minus infinity, so it's 0 times minus infinity. How do we get an indeterminate form limit evaluated? We use L'Hopital's rule, right? We're down to a limit of a function of one variable. So we use L'Hopital's rule and rewrite r as 1 over 1 over r. So this is the limit of ln of r over 1 over r, with the 2 pulled out. It's off the edge there. And if we can evaluate this limit, it comes out to be, it exists, a number, or it's infinity or minus infinity. If we take the derivative of the top over the derivative of the bottom, that's L'Hopital's rule, and the limit exists as a finite number, or is infinity or minus infinity, then that's the same as the limit of the original function. So let's take that. Derivative of the top is 1 over r, derivative of the bottom is minus 1 over r squared. And so we get this limit. Well, part of this cancels, right? And it's just the limit of minus r. Limit as r goes to 0 of minus r. Right, is 0, because it's a polynomial you plug in and get 0 times minus 2, the limit is 0 of this one. So here's how you can evaluate some of those, is make a change of variables to one variable. Well, what about if you think the limit doesn't exist? Now we have a harder time, right? Well, I mentioned earlier, just flying through here, and it's probably missed, that if the limit exists, then it has to exist along every path also that I didn't write up here. If the limit exists, then the limit along every path to that point exists and is the same number. So if you think it doesn't exist, all you have to do is show different paths, get different limits, and you know the limit doesn't exist, because if it did, it'd give the same limit, right? So here's this limit, xy over 3x squared plus 2y squared. It looks kind of innocuous, but unfortunately the same problem, 0, 0. The bottom's going to 0 and the top's going to 0. I wonder what the limit is. Maybe this is kind of looking like x times y, they're both going to be 0. Maybe it's 1, maybe this is 5 or something. Well, it's hard to tell. Let's try limits along different paths. Suppose we write a parametric path along the line y equals x will approach the 0 along this line, letting x equals t and y equals t, a parametric curve. Alright, so now that means if we take the limit along the path, we can use x equals t, y equals t in this equation. We'll take the limit as t goes to 0 of t times t, just replacing over 3t squared plus 2t squared, replacing both x and y with t. We've got the limit of t squared over 5t squared, which is just, oh, the t squareds cancel, it's 1/5, right? So the limit approaching the origin, 0, 0 along this path, the line y equals x, the limit is 1/5 exists. Now, if the limit of the function of two variables exists, then the limit along every path has to give that same number. Suppose we approach the origin along the x-axis this time. We could write that parametrically as x equals t, y equals 0. Along that path, then we get t times 0 on the top over 3 times t squared plus 2 times 0 squared. And look, the top is 0 no matter what point you're at along the x-axis. The top is always 0. So this quotient is 0 over 3t squared is the limit of 0, and the limit of 0 is 0. You don't say, oh, it's minus infinity or something because of t over t squared. These aren't canceling, it's 0 on the top for all t. And so this limit is actually 0. And here we have it. Coming along this path, the limit approaching the origin is 1/5, but coming along this path, either side, the limit is 0. And those two numbers aren't equal, so you simply say the limit does not exist. This shows that the two limits are different along the paths. All right, almost done. Calculus of functions of two variables. Now we mentioned continuity, we want to talk about continuous functions here. Suppose I want to know where this one is continuous. Remember all those important theorems like the mean value theorem, the intermediate value theorem, all those things depended on functions being continuous. We need functions of two variables to be continuous for the same reason. There will be lots of theorems for functions of two or more variables to be continuous. What's the region of continuity? Where is this function continuous? A lot of these are pretty easy to guess. It's mostly where they're defined. But let's be picky about this and make sure we do it right. Remember, a quotient of functions of continuous functions is continuous. And here's an algebraic expression. If you want to, an algebraic expression is a function that consists of arithmetic, powers, and roots. And so that's what this is, an algebraic expression. They will be continuous as long as you don't get a division by 0 or an even root of a negative. So in these kind of algebraic expressions, you just say, what's going to make the denominator 0 or make an even root of a negative? Well, we need this thing to be positive so that it won't divide by 0 or get an even root of a negative. This thing inside the square root to be positive. So we need 25 minus x squared minus y squared greater than 0